Today we're looking at writing formulas for binary ionic compounds. Just a reminder that an ionic compound occurs between a metal and a non-metal. The metal is the cation, which loses electrons, and non-metals are the anions, which gain electrons. Binary just means that it's a metal and a non-metal. Ternary would mean that it's metal and maybe two nonmetals. So today we're just looking at binary ionic compounds. Remember that a compound is a substance composed of two or more elements combined in a specific bond or ratio and held together by chemical bonds. Familiar examples of compounds are water and salt, sodium chloride. These are just reminders of chemical compounds. They're trying to get to the octet rule, so they want their outer energy levels to be full. In an ionic bond, atoms will gain or lose electrons in order to achieve the octet rule. For example, this oxygen only has 6 valence electrons. Once it gains 2 valence electrons, it becomes a -2 anion or oxide ion. Again, this happens when sodium loses an electron to become stable, nitrogen gains 3 electrons to become stable, and aluminum will lose 3 electrons to become stable. Just as a reminder, metals have between 1 and 3 valence electrons, and they have a loose hold on them because, it's much easier for them to lose those electrons than it is to get out here to try to gain 7 or 6 or 5 electrons. So they're just going to give them away, while the nonmetals have a pretty tight hold on their valence electrons, because they don't need as many to be complete. And so it doesn't take as much energy for them to gain, while noble gases have a very tight hold on their electrons and they don't bond at all. Again, you've got your metals on this side, your transition metals, your metalloids, and your non-metals. So the type of formula that we're focusing on writing today is ionic. Again, it's when a metal loses its valence electrons to a non-metals, and then the metal becomes a cation, which is positive, and the non-metal becomes a negative ion because it has gained electrons. So if you look at magnesium and oxygen, magnesium is a metal, oxygen is a non-metal, and so magnesium is going to give, it's in group 2, and it's going to give 2 electrons to that oxygen that needs 2 electrons in order to become stable. The same thing happens with sodium and chlorine. Sodium has a valence electron to give, and chlorine needs 2 because it's in group 6. So if you take 2 sodiums and bond them with 1 chlorine, you're going to get an ionic bond resulting in sodium chloride. So it's very easy to write binary ionic compounds. All you have to do is use the oxidation number that you can get off of the periodic table. Remember that the metal symbol is going to be written first, and it's going to have a positive oxidation number because it is losing electrons, while the non-metal is going to have a negative oxidation number because it is gaining electrons. Don't forget that when you're talking about metals, you look at the group number, and that tells you how many electrons they're going to give away. But when you're talking about non-metals, you look at not the group number, but you look at how many it needs to gain in order to become complete, and that will be a negative number. For example, all of the elements in group 7 they have 7 valence electrons, and they need 1 to be complete. So their oxidation number is -1. Another way to think about ionic charges, and I know we've written this on our periodic table, but your metals always have a plus. So group 1 is +1, group 2's oxidation number is +2, and group 3 is +3. Now remember, these are all of your metals, and they are going to give this number of electrons away. But when you look at the nonmetals, their oxidation number becomes how many valence electrons they need to be complete. So for example, all of the elements in group 15 have 5 valence electrons. They need 3 negative charges or electrons to become complete. In group 6, they all have 6 valence electrons, and they need 2 negative charges or 2 electrons to be complete. And in group 17, they all have 7 valence electrons, and they need 1 negative charge or 1 negative electron to be complete. So with the metals, you just look at their group numbers, and it's a plus whatever their group number is. That's how many they're going to lose. But when you get to the nonmetals, then you start looking at how many they need to gain to be complete, and that is their charge number. Again, you can see the same thing. All of your metals have plus numbers. Group 1 +1, group 2 +2, group 3 +3. That's how many they're going to give away. But when you switch over to the nonmetals, then you are looking at how many they need to gain, how many negative charges they need to gain to be complete. Okay, so it's very simple to write the chemical formulas. So the element to the farther to the left always appears first, except for hydrogen. So basically you're looking at your metal, the symbol for your metal always being written first. If there is a hydrogen, it's going to go at the end unless the element is nonmetals. So if the element is a metal, then it'll be the metal followed by the hydrogen. But if it's nonmetals, it will be the hydrogen will come first, followed by the nonmetal. Like the example H2O. Hydrogen comes first, followed by the nonmetal oxygen. Okay, so now we're going to look at crisscross applesauce. It's very, very simple procedure. In order for these compounds to be a neutral, then their charges have to balance out. And so when you look at, for example, aluminum oxide, aluminum is in group 3, so it has a +3 charge, and oxygen is in group 6, so it has a -2 charge. All you have to do is write those charges as superscripts, which means that they are above the element. And so in order to get the correct formula, all you have to do is crisscross those superscripts and make them subscripts. So where you had Al +3 and O -2, now you have Al2O3. And if you add the charges up, then it all becomes neutral. Let's look at some more examples. So here's basically your 5 steps for crisscross applesauce. You write the symbols of the 2 elements first. You always write the symbol of the metal first. And then you write the valence of each as superscripts. So that means that the number is going to be plus if it's a metal, and it's going to be above the element symbol. And then if it's a non-metal, it's going to be a negative, and it's going to be written above. So all you have to do is then drop those positive and negative signs and crisscross the superscripts so they become subscripts. And whenever you can, you reduce. Well, let's look at an example. One more thing. If the charges are of equal value, then you don't really write anything. So let's say you've got Al +3 and P -3. We have a +3 and a -3, so you don't write anything. So the chemical formula would just be ALP. So again, step 1, write the symbols of the two elements. The metal goes first. Step 2, write the valence charge or the oxidation number for each element as superscripts. So boron's charge, it's in group 3, so it's a +3. Oxygen is a -2. So you just write those as superscripts. Step 3, you just drop that positive and negative sign. So now we've got boron with 3 as a superscript and oxygen as 2 as a superscript. Step 4, you just crisscross them. So you take that 3 that was by boron and move it behind oxygen. Take that 2 that was behind oxygen and move it behind boron. And this is your correct formula, B2O3. Now, if it was 2 of the same, like B2O2, then you would not write anything. You would just write BO. So you reduce whenever you can. Here's some more examples. If SR2O2, you don't have to write those two. That reduces to SRO. AL3P3 reduces to ALP3. PB2O4 reduces to PBO2. And BA3N2 just doesn't reduce. So if it reduces, then you reduce, and if it doesn't, you just write it like it is. So just in summing up, ionic bonding occurs between a metal and a nonmetal. Metals lose all their valence negative electrons and become cations. Nonmetals gain enough electrons to fill their valence level and become anions. You always crisscross valences and reduce to determine the formulas of ionic compounds. Do not use prefixes in the names. And ions always form that crystal lattice shape or crystal structure like sugar or salt.